Beneath a sky swollen with relentless clouds, rivers overflowed, and plains became endless sheets of water, sculpting a world unlike any we know. 2 million years of unbroken rainfall transformed continents, fusing rivers, lakes, and wetlands into vast, liquid labyrinths where life was both challenged and remade. Forests drowned, amphibians thrived, and early reptiles struggled to survive in a landscape dominated by water's constant pulse. Every drop reshaped the land, rewrote ecosystems, and tested the limits of adaptation. Journey now into this ancient deluge and witness a planet drenched for millennia, where survival was dictated by rain itself. The storms that wouldn't stop. The first drops fell not as a gentle warning, but as a herald of transformation, hammering ancient landscapes with a persistence that defied the cycles of day and night. Across the equatorial supercontinent of Pangaea, the air thickened with humidity, reaching saturation levels approaching 100% in some lowland basins, while massive convective cells towered over forests that had never seen such weight pressing from above. Evidence from paleosols in modern-day northern Italy and the Dolomites shows layers of clay and silicate deposits forming in rapid succession, indicating that rainfall rates frequently exceeded 1 meter per month, a tempo of precipitation that would be catastrophic for even the hardiest Triassic flora and fauna. The atmospheric destabilization was amplified by the sudden influx of greenhouse gases from volcanic outgassing, particularly CO2 and SO2, whose concentrations have been measured in carbonate nodules to have spiked several hundred parts per million above baseline, fundamentally altering the thermodynamics of the lower atmosphere. Beneath these swollen skies, the first storms were born from the interaction between rising warm air currents and the unusually humid planetary boundary layer. Geological cores from Wrangellia basalts in western Canada indicate that episodic eruptions coincided with peaks in rainfall intensity, linking volcanic events directly to the hyperactive hydrological cycle. Convection cells in these early storms often reached 20 kilometers in altitude, with thunderheads so vast that lightning discharges occurred not in sporadic flashes, but as near continuous electrical storms, as inferred from fulgurite deposits preserved in sedimentary sequences. The chemical signatures of these storms, recorded in sulfur isotope ratios, suggest that these were not ordinary storms. They carried acidic components capable of accelerating weathering, providing the first hints that rainfall itself would begin to reshape continents at unprecedented rates. On the ground, forests that had persisted for millions of years faced the immediate consequences. Dendrochronological reconstructions from silicified logs in the Alps reveal stunted growth rings, interrupted by repeated flooding events, while spores and pollen trapped in the clay-rich paleosols show abrupt declines in gymnosperm diversity. Ferns and lycophytes, more tolerant of waterlogged conditions, surged in abundance, creating patchworks of green that thrived in the muddy, light-starved understory. Even the largest Triassic conifers, some exceeding 40 meters in height, struggled to maintain vertical growth under the weight of constant precipitation, while their fallen needles contributed to anaerobic soils that would later fossilize as black shale layers. These layers are not just geological curiosities. They preserve chemical evidence of mineral leaching and early carbon sequestration that hints at how rainfall began influencing the global carbon cycle from the very first days of the Carnian pluvial event. Fauna, too, were immediately challenged by the atmospheric upheaval. Trackways preserved in floodplain mudstones from southern Germany reveal that archosauriforms and early dinosauriforms were forced onto elevated landforms to avoid inundation, with many juveniles failing to survive the rapidly expanding wetlands. Predators such as erythrosuchids and rauisuchians faced drastically altered hunting grounds, their usual ambush strategies confounded by rivers that could swell hundreds of meters in width within days. Fossilized gut contents suggest opportunistic feeding strategies emerged quickly, including scavenging behaviors in species previously thought to rely solely on active predation. The interplay between atmospheric dynamics and terrestrial survival is clear. A world that had once been stable now demanded rapid behavioral and physiological adaptation, even from apex species. Oceanic currents began responding almost simultaneously to the rainfall. Sediment cores from the Tethys margin indicate rapid influxes of terrigenous material, with silt and clay layers showing distinct seasonal banding that corresponds with volcanic pulses. This influx diluted coastal salinity and stressed marine communities, leading to early signs of localized anoxia in lagoonal environments. Fossils of coelacanths and temnospondyl amphibians in these layers suggest that some species were already beginning to exploit the expanding network of freshwater-dominated coastal systems, highlighting the early ecological opportunities created by the persistent storms. The link between atmospheric destabilization and the rapid transformation of nearshore habitats underscores how intimately the hydrological, terrestrial, and marine systems were entwined from the very beginning of this extreme climate event. Evidence from tree ring isotopes and sedimentary carbonates also reveals subtle but significant shifts in oxygen isotope ratios, demonstrating that even regional temperature gradients were altered by the constant moisture flux. Areas that had previously experienced pronounced dry seasons now remained consistently damp, with microclimates stabilizing around near-saturated humidity. This persistent wetness not only affected vegetation growth patterns, but also the reproductive cycles of amphibians and early reptiles, which were highly dependent on ephemeral water bodies. Fossilized eggs and embryonic remains from temnospondyls show growth interruptions indicative of fluctuating water levels, suggesting that reproductive success was already being mediated by the relentless storms, creating an invisible filter on the populations that would survive the next millions of years. Lightning strikes, mud flows, and acid-laden raindrops combined to create microgeological crises in real time. Sedimentological evidence from braided channels in modern-day Austria indicates that the storm's energy could mobilize tens of cubic kilometers of sediment within decades, reconfiguring floodplains and river networks faster than ecosystems could stabilize. Large-scale depositional features, such as megafans, formed in the basins adjacent to volcanic highlands, while erosional unconformities record abrupt changes in flow direction and channel incision. The combination of high precipitation, unstable substrate, and acidic runoff not only sculpted the landscape, but also accelerated the cycling of nutrients, creating a feedback loop in which the storms themselves maintained their own intensity by continuously modifying surface conditions. By the time the first million-year phase of this relentless rainfall was underway, it had become clear that Earth was entering an entirely new climatic regime. The interplay between volcanic outgassing, supersaturated air, and constantly saturated soils created a self-reinforcing system in which storms could persist indefinitely. Observed in the stratigraphic record as tightly stacked mudstone layers, coupled with carbon and sulfur isotopic excursions, these data illustrate that the very engines of the atmosphere had been rewired. Vegetation clung desperately to narrow patches of stable ground, while fauna adapted, perished, or migrated. Rivers expanded into labyrinthine wetlands, and coastal seas bristled with sediments freshly torn from the land. Each element, sky, soil, water, and life, was locked into a hydrological pulse that would not relent. In this suspended world, the storms were no longer merely weather. They were a planetary force, their persistence setting the stage for the geological, chemical, and ecological mechanisms that would keep them alive and shape the unfolding transformations of Earth's enduring wet epoch. The volcanic fuel pumping water into the sky. A towering column of molten rock fractures the sky, erupting from fissures in the Rangelia Large Igneous Province and releasing plumes that will forever alter the chemistry of the atmosphere. From paleogeographic reconstructions, these volcanic pulses stretched for thousands of kilometers, their basaltic flows spilling across lowlands, igniting local fires, and injecting prodigious quantities of greenhouse gases into the air. Carbonate nodules preserved in Triassic paleosols indicate CO2 concentrations increased by hundreds of parts per million in less than a millennium, creating a potent thermal forcing that directly amplified the intensity of ongoing storms. At the same time, sulfur dioxide, trapped in mineral veins and later measured isotopically, began forming aerosols that scattered sunlight, producing regional cooling pockets, while the surrounding atmosphere remained superheated, a paradox that destabilized convection patterns and fed the relentless rain. Measurements from sediment cores and ash layers reveal that each eruption coincided with dramatic spikes in rainfall, suggesting a causal link between volcanic activity and hydrological amplification. Fine ash drifting over floodplains coated soils with chemically reactive particles, increasing their albedo and subtly altering evaporation rates from lakes and rivers. In regions corresponding to modern Western Canada and the eastern United States, repeated lava flows deposited layers several meters thick in a matter of decades, while palynological evidence shows that fern spores and lycophyte pollen surged in response to nutrient influxes, reflecting an ecosystem already adapting to the chemical and hydrological shocks. The eruption-driven pulses of gases and particulate matter ensured that convection cells in the lower atmosphere remained highly energetic, providing the kinetic force that kept storms from ever breaking. Sulfur aerosols played a particularly insidious role, suspending in the stratosphere and scattering incoming solar radiation. These suspended particles not only reflected heat into space, but also interacted with water vapor to create microscopic condensation nuclei, intensifying cloud formation and prolonging precipitation events. Isotopic ratios of sulfur preserved in shale sequences show repeated excursions corresponding to eruption pulses, indicating that these aerosols were not transient but persisted for decades, feeding the self-sustaining atmospheric engine. In combination with CO2-induced greenhouse heating, the atmosphere became a system in which rising moisture-laden air continuously collided with cooler strata, producing near-constant thunderstorms with thunderheads reaching 20 kilometers high, a scale previously unseen in the Triassic. Thermal anomalies recorded in sedimentary basins adjacent to Rangelia flows demonstrate that surface heating accelerated evaporation from rivers, lakes, and newly formed wetlands. This feedback loop between volcanic heating and moisture supply created a situation in which storms were not merely persistent but self-reinforcing. Rivers swelled beyond their banks on a nearly monthly basis, depositing massive layers of silt and clay downstream while reshaping floodplains into sprawling wetlands. Even short-term eruptions could trigger extreme flooding events, with sedimentological evidence showing tens of cubic kilometers of material mobilized in single episodes. The cumulative effect over millennia transformed regional topography, creating labyrinthine channels, megafans, and sediment-laden deltas that served both as conduits for stormwater and as visual records of the enduring rainfall. Plume dynamics, inferred from paleogeography, suggest that gases from individual eruptions rose to altitudes exceeding 20 kilometers, penetrating the lower stratosphere and mixing with tropospheric moisture. This vertical mixing ensured that water vapor, sulfur compounds, and CO2 were distributed over continental scales, priming the atmosphere for near-global storm formation. Lightning frequency increased dramatically in response to this hypercharged convection, with fulgurite evidence from contemporaneous sediment beds showing networks of fused silica that attest to repeated electrical discharges. These storms were not local anomalies. They represented an atmospheric engine of continental magnitude, with volcanic activity as its persistent fuel, keeping the hydrological system locked in motion for millions of years. Radiometric dating of Wrangellia lava flows provides a temporal framework, revealing eruption pulses spaced over hundreds of thousands of years, each coinciding with spikes in rainfall intensity and sediment deposition. Chemical analyses of carbonate nodules indicate corresponding CO2 fluctuations, while sulfur isotope studies confirm repeated aerosol dispersal events. Together, these data reveal a system in which the atmosphere and lithosphere were intimately coupled, with volcanic activity directly orchestrating the hydrological intensity that had become the hallmark of the Carnian pluvial event. This geological choreography demonstrates that the storms witnessed on Pangaea were not isolated meteorological phenomena, but the product of planetary-scale volcanic forcing. The biosphere responded almost immediately. Wetlands expanded into newly deposited basins, creating refugia for amphibians like metaposaurids and temnospondyls, which thrived in constantly saturated habitats. Early archosaurs and proto-dinosaurs were forced to navigate treacherous terrain as rising rivers cut across migration routes and nesting grounds. Fossil trackways show altered locomotion patterns, with track spacing indicating slower, cautious movement through mud-laden floodplains. Vegetation adapted to the high rainfall and chemically enriched soils. Ferns, lycophytes, and hydrophilic gymnosperms proliferated, while conifers struggled with waterlogged roots. In essence, life on land and in nearshore waters was shaped by the volcanic pulses, with survival contingent on the ability to endure chemically and physically transformed environments. Even oceanic systems were influenced. Terrigenous sediments carried from volcanic highlands rapidly accumulated in coastal basins, creating localized anoxic zones that stressed marine organisms and altered nutrient cycling. Black shale layers and isotopic anomalies in tethys sediments record these influxes, connecting terrestrial eruptions with marine ecological consequences. Evaporation from volcanic heating contributed to freshwater fluxes into estuaries and inland seas, maintaining low salinity conditions that further influenced coastal biodiversity. This interconnected system, in which volcanism, atmosphere, and hydrosphere interacted continuously, ensured that the storms could remain unstoppable, sustained not just by existing moisture, but by the very forces reshaping Earth from within. The storms were only the visible expression of a planetary engine fueled by fire and gas, with Wrangellia eruptions driving the hydrological pulse through greenhouse warming, aerosol scattering, and atmospheric charging. The interplay between eruptions, evaporation, and convective storms illustrates that precipitation was no longer a passive phenomenon. It was actively orchestrated by volcanic processes. Vegetation clung to nutrient-enriched soils while animals navigated flood-ridden terrain, and rivers and coasts bore witness to the planet's relentless re-engineering. The volcanic fuel had been poured into the sky, supercharging the rain and setting the stage for landscapes to be sculpted into mud-laden floodplains, labyrinthine wetlands, and sediment-choked rivers, a dramatic transformation that will continue as Earth's surface responds to the perpetually saturated world. Hyper-erosion, when continents turned to mud. Rainwater hammered the ancient slopes with unrelenting force, turning stable soil into liquid sediment that surged toward the lowlands. Hillsides that had once supported forests of conifers and seed ferns now collapsed into muddy torrents, carrying with them the remnants of fragile vegetation. Stratigraphic evidence from the Carnian pluvial event shows that these sediments accumulated rapidly, forming layers of mudstone up to several meters thick in only a few thousand years. Geochemical analysis of these deposits reveals elevated clay mineral content, suggesting continuous chemical weathering under high humidity and near constant rainfall. Fossilized root traces indicate that plants struggle to anchor themselves, with only resilient swamp-adapted species managing to survive in the saturated soil. Rivers, once predictable arteries of the landscape, fractured into braided channels, spilling their contents across sprawling floodplains. Avulsion events occurred with remarkable frequency, rerouting entire drainage systems within decades. Sediment transport models based on fossilized channel widths estimate that flows exceeded 10,000 cubic meters per second in some lowland basins, comparable to the largest modern rivers, but sustained for centuries at a time. Isotopic ratios of carbon and oxygen in these deposits show repeated pulses of freshwater input, confirming that rainfall was unbroken over millennia. The constantly shifting river networks left behind labyrinthine wetlands that became new ecological arenas for amphibians, fish, and invertebrates. Sediment fans expanded like living tapestries, capturing the violent history of millennia in layered clays and sands. Megafans tens of kilometers wide, formed as materials from the highlands, were redistributed across flat terrain. Grain size analysis indicates periodic bursts of coarse sediment deposition, likely caused by extreme storm events linked to volcanic forcing. Fossil shells of freshwater bivalves embedded in these fans show rapid colonization of newly deposited sediment, illustrating how life adapted quickly to unstable substrates. Palynological studies reveal spikes in fern spores, confirming that these mud-laden plains were hotspots for pioneer plant species thriving in constantly disturbed soils. Exposed bedrock on mountain flanks revealed fractures widened by the constant barrage of water and chemical dissolution. Joint spacing in Triassic sandstones indicates that freeze-thaw cycles were augmented by waterlogged conditions, promoting rock collapse. Geochemical signatures of silicic acid released into streams support the theory that silicate weathering was dramatically accelerated during this period. Local relief was actively reduced as hills eroded, feeding sediment downstream and reshaping drainage networks. The combination of mechanical and chemical erosion produced sediment layers, later identifiable as markers of extreme climatic stress in the fossil record. Silicate weathering accelerated, leaching minerals into waterways and transforming the chemistry of soils and rivers alike. Concentrations of dissolved calcium, magnesium, and silica in paleosols suggest massive chemical fluxes, contributing to shifts in water, pH, and nutrient availability. These chemical changes would have influenced both terrestrial and aquatic ecosystems, favoring species able to tolerate low oxygen and high mineral conditions. Modern analogues in tropical rainforest catchments show that such weathering can mobilize hundreds of tons of silicate minerals per square kilometre per year, providing a scale for interpreting the Triassic rainfall event. Evidence from carbon isotope excursions in marine sediments suggests that these weathering processes also played a role in modulating atmospheric CO2 levels over millennial timescales. Vast wetlands emerged in depressions scoured by torrents, creating new habitats for opportunistic flora and fauna. Fossil evidence from central Pangaea indicates that large temnospondyl amphibians thrived in these wet basins, while early reptilian species occupied raised patches of slightly drier ground. The proliferation of ferns, horsetails, and lycophytes created dense, water-tolerant vegetation, which stabilized portions of the landscape and slowed localized erosion. Invertebrate fossils, including giant arthropods and freshwater bivalves, are found in abundance, reflecting the ecological richness that emerged despite or because of the constant hydrological disturbance. Pollen and spore assemblages suggest that some species relied entirely on these wetlands for reproduction, showing a strong link between persistent flooding and biodiversity patterns. Mud-choked channels forced terrestrial animals to reroute their migrations, leaving tracks preserved in soft sediment that would fossilize for eons. Theropod and prosauropod trackways, distorted by waterlogged substrates, indicate repeated attempts to navigate treacherous terrain. Large amphibians, including metoposaurids, appear to have exploited the saturated floodplains for hunting, leaving dense concentrations of footprints that reflect both predation and escape behaviours. Sedimentology studies show that repeated flooding events buried these tracks quickly, creating stratigraphic sequences that offer an unprecedented record of Triassic life responding directly to continuous rainfall. These traces reveal both behavioural flexibility and the physical challenges imposed by an ever-shifting landscape. Fine layers of mudstone and conglomerate record the relentless grinding of continents under a sky that never ceased to pour. Cyclostratigraphy reveals rhythmic deposition patterns, suggesting that storm intensity fluctuated seasonally, yet never paused long enough for soils to stabilize fully. Analyses of paleocurrent directions in conglomerates show that sediment was redistributed over hundreds of kilometers, producing fan-shaped deposits that bridged basins. Trace fossils indicate that aquatic organisms colonized these muddy plains immediately after sedimentation, demonstrating rapid ecological resilience. The sedimentary record preserves chemical signatures of repeated rainfall pulses, including elevated sulfur and carbon isotopes linked to volcanic emissions, providing a multi-proxy view of the interplay between atmospheric forcing and surface processes. Every downpour amplified the reshaping of the surface, linking atmospheric intensity directly to the planet's geological transformation. Hydrological models suggest that sustained rainfall increased erosion rates by 10-50 times those in modern analogues, producing sediment loads capable of suffocating nearby rivers and lakes. Channel incision, slope collapse, and deltaic expansion all occurred in concert, showing that landscapes were responsive to both climatic and volcanic triggers. Fossil evidence confirms that terrestrial species were continually challenged to adapt, seek refuge, or perish, while plants and aquatic organisms took advantage of newly formed niches. The codependence of rain and erosion demonstrates that the Earth's surface was a dynamic participant in a larger planetary system, continuously moulded by atmospheric and volcanic processes. In this landscape of constant motion, Earth's terrain became both canvas and witness to the endless hydrological forces, setting the stage for life to navigate a perpetually wet world. Mud-laden floodplains, braided rivers, and freshly exposed soils created a planetary laboratory in which evolution unfolded in response to a sky that never relented. The stratigraphic record preserves this interplay, showing that erosion, sedimentation, and ecological adaptation were inseparable during this epoch. As the landscape continued to be sculpted, the stage was prepared for subsequent chemical and ecological transformations, revealing how unbroken rainfall could not only rewrite the surface of the Earth, but also influence the trajectory of life across entire continents. Air you could almost swim through. Above the sprawling floodplains, the sky thickened with moisture until the sun itself struggled to penetrate the vapor-laden canopy. Triassic skies were unlike any modern comparison, with humidity levels approaching near saturation across vast continental interiors. Measurements of paleosol mineralogy indicate that water retention in the atmosphere exceeded modern tropical rainforests by several factors, producing a blanket of heavy, charged air. The combination of persistent cloud decks and warm, saturated air generated convective instability, allowing storm cells to tower for kilometers above the land, their bases blending seamlessly with the mist rising from the flood-ridden plains. Towering convective columns erupted from the surface, their rising cores charged with latent heat and energy drawn from unceasing rainfall. Volcanically enhanced warming had supercharged these processes, allowing small differences in temperature and moisture to rapidly amplify vertical airflow. Modern atmospheric models scaled to Triassic CO2 concentrations suggest these convective systems could reach up to 15 kilometers in height, producing turbulence far exceeding contemporary storm systems. The constant vertical transport of water vapor and heat maintained the supersaturation of air, making each storm a self-reinforcing atmospheric engine. Lightning streaked across cloud decks in unprecedented frequency, leaving telltale impressions in fossilized soils that scientists now decode as paleoelectric signatures. Microscopic spherules of fused silica and localized charred plant material indicate that intense electrical discharges were common even in low-lying areas beneath thick cloud layers. Analysis of paleosoils from northern Pangaea reveals concentrated patterns of fulgurites, suggesting that the energy of these storms reshaped the chemical and physical properties of surface soils. Lightning thus served not only as a visual spectacle, but also as a geochemical agent, altering nutrient distributions across landscapes already saturated with water. Humidity approached saturation, transforming air density and creating a medium in which even small organisms experienced drag as though moving through water. Fossilized trackways of early reptiles show signs of altered stride and gait, likely influenced by the dense, moisture-laden air, while invertebrate exoskeletons indicate adaptations to high humidity environments. Atmospheric pressure anomalies from trapped moisture likely affected respiration in amphibians and other small vertebrates, further shaping survival strategies. Paleoclimatic models suggest that relative humidity remained above 90% for decades at a time, creating a near-constant challenge for terrestrial organisms. Isotopic analysis of Triassic mudstones reveals oscillations in oxygen and hydrogen ratios, painting a portrait of a perpetually charged atmosphere. These delta to the power of 18O and delta D excursions correlate with known volcanic outgassing events, showing that each pulse of CO2 and aerosols reinforced the atmospheric saturation. Sediment cores indicate that water cycles were tightly coupled with surface and subsurface hydrology, ensuring that precipitation never fully ceased. The isotopic evidence provides a timeline of how atmospheric chemistry evolved in parallel with erosion, river restructuring, and biological adaptation, demonstrating a planet in which sky, soil, and water were inseparable actors. The interface between clouds and land became a theatre of chemical exchange as sulfur and carbon aerosols redistributed nutrients across continents. These aerosols enhanced cloud condensation nuclei formation, intensifying rainfall and influencing storm trajectories. Analyses of trace metals in sedimentary layers suggest that volcanic emissions were not confined to local areas. Instead, they were transported hundreds of kilometers, fertilizing floodplains and wetlands. The chemical interplay between volcanic output and hydrological cycling also contributed to the acceleration of silicate weathering, tying atmospheric dynamics directly to surface erosion and nutrient flux. Plant canopies, already struggling in soggy soils, faced additional challenges as condensation dripped incessantly, altering microclimates beneath the leaves. Ferns, horsetails, and early conifers developed adaptations such as thickened cuticles and specialized leaf arrangements to shed excess water. Paleobotanical studies show that dense canopies trapped humidity near the ground, amplifying fungal growth and decomposition rates. This microclimate effect not only influenced plant survival, but also determined the spatial distribution of insect and amphibian populations, showing the interdependence of air chemistry, rainfall, and life. Storm persistence created feedback loops, with evaporation from flooded plains feeding cloud regeneration in a cycle that never fully abated. Hydrological modelling indicates that vast wetland surfaces contributed enormous amounts of moisture to the atmosphere, reinforcing the density and saturation of the air above. Lightning, wind shear, and convective updrafts ensured that these storms could persist for years, forming semi-permanent cloud decks over entire regions. Each feedback loop magnified the ecological pressure on terrestrial ecosystems, shaping migration patterns, predator-prey interactions, and species survival in a world dominated by water. Bird's-eye fossil impressions, preserved in flattened vegetation mats, suggest that even small animals experienced atmospheric drag and altered locomotion patterns. Tracks and body impressions indicate that some amphibians and reptiles moved cautiously, pausing frequently in high humidity zones to conserve energy. Aquatic species benefited from stable water tables, but still faced turbulent surface conditions, while terrestrial fauna evolved behaviors to cope with the extraordinary resistance and wetness of the air. The fossil record preserves these subtle adaptations, highlighting how the atmosphere itself became a selective pressure influencing evolutionary pathways. Within this elevated aerial domain, the atmosphere shaped life, energy, and chemical cycles, setting the stage for the terrestrial world's next ecological upheaval. The supersaturated atmosphere was inseparable from the flooded landscapes below, with each storm reinforcing sedimentation patterns, chemical cycles, and ecological networks. By linking the behavior of the air above to the life and land beneath, this narrative underscores how continuous rainfall reshaped the planet at every scale, setting the stage for vegetation collapse, faunal adaptation, and the next wave of environmental transformation that would define the epoch: drowned forests and collapsing ecosystems. Waterlogged trunks sagged under their own weight, roots drowning in a soil that had lost all capacity to breathe. Across vast floodplains, towering conifers and early gymnosperms clung desperately to patches of elevated ground, but persistent rainfall ensured that most root systems remained submerged, triggering widespread tree mortality. Fossilized stumps, logs, and leaf mats from this era reveal a landscape in which canopy collapse was frequent, creating a mosaic of light-starved understories and open wetlands. The constant saturation not only inhibited photosynthesis but also promoted anaerobic soil conditions, fundamentally altering nutrient availability and challenging every organism anchored to the land. Hidden networks of fungi transformed fallen wood into rich humus, accelerating nutrient cycling beneath stagnant waters. Mycorrhizal, and saprotrophic fungi thrived in these oxygen-depleted soils, decomposing plant matter at unprecedented rates and releasing large pulses of carbon dioxide back into the atmosphere. These biological processes were recorded in coalified plant remains, charcoal fragments, and geochemical markers within the sediment, illustrating how microbial activity amplified the effects of relentless precipitation. The decomposition also enriched local soils, paradoxically creating fertile patches that would later become refuges for wetland plants able to tolerate prolonged inundation. Spore-bearing plants claimed territory once dominated by towering conifers, their fronds creating dense green carpets over the floodplain. Ferns, horsetails, and lycophytes expanded explosively, forming continuous mats that trapped water, sediment, and organic debris. Palynological data show sharp increases in fern spores and a concurrent decline in gymnosperm pollen, highlighting the ecological shift. These plants not only tolerated the saturated environment but also actively reshaped it, their dense roots and rhizomes stabilizing soft sediments while further reducing oxygen penetration into soils, a feedback loop that reinforced wetland dominance. Swamp basins thickened with layers of peat and mud, capturing frozen moments of life and decay for millions of years. Stratigraphic sequences from this period reveal tightly laminated mudstones and coal seams interspersed with plant macrofossils, preserving snapshots of ecological communities. The accumulation of organic matter in low-lying depressions slowed decomposition in deeper layers, effectively storing carbon and altering local chemistry. Some of these wetland deposits reveal plant assemblages intermixed with insect cuticles and amphibian remains, illustrating how entire food webs became anchored to saturated zones. Such depositional environments became laboratories for evolutionary experimentation, supporting new microhabitats where only specialized flora and fauna could survive the continuous inundation. Chemical pockets of hydrogen sulfide spread through submerged soils, creating lethal zones for less adapted vegetation. Anaerobic bacteria thrived in waterlogged sediments, producing sulfur compounds toxic to roots and further reducing plant survival. Geochemical analyses of sediment cores indicate that these toxic pockets were widespread, shaping patterns of plant mortality and survival. The presence of sulfide-tolerant species alongside decimated conifers provides a stark testament to how biogeochemistry directly sculpted ecosystems under unending rainfall. Even early lycophyte and horsetail species exhibit anatomical adaptations, hollow stems and air canals, suggesting selective pressure from chemically stressed and saturated soils. Shifts in carbon ratios within sediments reveal how expanding wetlands influence the atmosphere over geological timescales. Radiocarbon proxies and delta to the power of 13 sea excursions indicate that the burial and decomposition of vast plant biomass significantly altered atmospheric carbon concentrations. This interplay between biological activity and geochemical cycles demonstrates that even localized ecosystem changes had planetary implications, feeding back into global climate dynamics. Continuous rainfall not only reshaped the landscape, but also became a driver of Earth's chemical evolution, linking surface processes with atmospheric composition in profound ways. Flooded understories became labyrinths of water channels and collapsing vegetation, shaping habitats for only the most resilient species. Fallen branches and submerged roots created complex microhabitats for early amphibians, arthropods, and small reptiles. Trace fossils show distinctive movement patterns as organisms navigated sticky mud, ephemeral pools, and shifting plant debris. These environmental pressures drove behavioral and physiological adaptations, with species exploiting the unstable terrain for shelter, hunting, or reproduction. Insects, including giant Triassic beetles and early odonates, thrived among floating mats of vegetation, forming critical links in detritus-based food webs. Amphibians and small reptiles adapted locomotion strategies to navigate constantly saturated terrain, leaving behind distinct trace fossils. Temnospondyle amphibians and early archosauriforms appear in trackways crossing semi-flooded plains, their limb morphology suggesting powerful strokes and broad paddling movements. Fossil evidence shows seasonal aggregation in slightly elevated areas, indicating that these species actively sought micro-refugia to survive both predation and flood hazards. These adaptive strategies reveal how faunal life responded dynamically to the pressures imposed by continuous rainfall. Clusters of emergent plants formed oases amidst the inundated plains, sustaining pockets of diverse microfauna. Small islands of resilient vegetation became critical nodes in the otherwise water-dominated landscape, supporting insect populations, amphibians, and early reptiles. Macro and microfossils from these patches indicate concentrated biodiversity, with specialized species coexisting in highly competitive but stable microenvironments. Sediment chemistry suggests these islands also acted as nutrient traps, providing localized boosts that allowed some species to maintain stable populations despite the omnipresent floods. Predation and foraging strategies are adapted to these wet conditions in remarkable ways. Amphibians evolved ambush tactics from shallow water, small reptiles scavenged decaying plant matter along emergent banks, and insects exploited submerged detritus. Fossilized gut contents and trace fossils indicate that organisms had to exploit both terrestrial and aquatic niches simultaneously, blurring the lines between land and water. These behaviors not only allowed species to survive but also reshaped ecological interactions, creating novel food webs uniquely tied to the perpetually wet environment. Beneath the endless sheets of rainfall, ecosystems were rewritten as only the most flexible forms of life endured. The collapse of forests, the proliferation of wetlands, and the rearrangement of food webs created a world where survival depended on adaptability, mobility, and tolerance of chemical and physical extremes. In this landscape, the line between life and death was defined by water, and each organism became both witness and participant in a planetary-scale experiment. As these drowned ecosystems matured, they laid the groundwork for new evolutionary trajectories, foreshadowing how animals would recalibrate hunting, foraging, and reproduction in the face of unrelenting environmental stress. A story that continues in the lives of creatures forced to navigate this permanently wet world, hunting, feeding, and surviving in a flooded world. The mud beneath every step shifted unpredictably, forcing predators and prey alike to rethink the basic mechanics of movement. Footfalls sank deeper than expected, and soft substrates transformed ordinary locomotion into a calculated effort, where every stride could mean survival or sudden entrapment. Trackways, preserved in the fossil record, reveal a world where dinosaurs, archosaurs, and giant amphibians navigated terrain that was part land, part water, and wholly unstable. Limb proportions show subtle adaptations: stronger forelimbs for traction, broader feet for weight distribution, and sometimes elongated toes to prevent sinking, all evolving under the relentless pressure of 2 million years of rainfall. The hydrological pulse had reshaped not only landscapes, but the very anatomy of creatures that walked upon them. Puddles and shallow channels dictated the routes of migration, often channeling entire populations into tight corridors of survival and conflict. Seasonal rises in riverbeds could cut off traditional pathways, forcing large herbivores to detour through dangerous waters where predators waited in ambush. Even small creatures had to navigate treacherous wetlands where vegetation, density, and water depth combined to form natural traps. Fossilized ripple marks and sediment imprints confirm that these temporary channels were high traffic zones, worn not only by the movement of countless animals, but also by the erosion of fine mud under persistent wet conditions. Sharp eyes and heightened senses became essential as visibility dropped under dense, storm-darkened canopies. Shadows flickered in the constant drizzle, while fog rising from saturated soils blurred distances, masking predators and prey alike. Sensory adaptations appear in the fossil record: forward-facing eyes for depth perception, enhanced olfactory regions for detecting food or danger, and auditory adaptations for interpreting sounds through water-laden forests. These traits allowed species to anticipate encounters, track prey, and avoid predation in conditions that would overwhelm less specialized animals. Amphibians like Metoposaurids exploited water-filled depressions, ambushing prey in sudden, calculated bursts. Their flattened skulls and dorsally positioned eyes allowed them to lie submerged, invisible beneath still water, while limbs and tails generated rapid propulsion. Fossil bone beds suggest that population densities of these amphibians peaked in areas where small floodplain ponds remained connected during rains, providing both hunting grounds and protection from terrestrial predators. In this world, ambush predation was not just a tactic, but a necessity, refined over generations in response to environmental constraints imposed by constant water saturation. Fossil trackways reveal distortions where massive reptiles sank ankle-deep in saturated soils, highlighting the biomechanical stress of constant flooding. Prints are sometimes doubled, smeared, or overlapped, indicating sudden slips, repeated corrections, or struggles to maintain balance. These distortions offer insight into gait, stride length, and weight distribution, revealing how body design intersected with environmental challenges. Even for apex predators, moving across the mud was a constant negotiation, balancing the need to hunt efficiently with the risk of becoming trapped or exhausting energy reserves too quickly. Riverine predators adapted new hunting strategies, combining stealth with the selective use of submerged vegetation as cover. Crocodilomorph precursors, smaller archosaurs, and semi-aquatic reptiles learned to exploit the interface of land and water, striking from reeds, fallen logs, and shallow pools. Fossilized stomach contents, bite marks on bones, and sedimentary evidence show repeated patterns of ambush near channels where prey congregated. Predation was therefore deeply intertwined with the hydrological architecture of the land. Where water flowed or pooled, life and death followed predictable yet perilous paths. Juvenile survival rates fluctuated dramatically, as smaller creatures were both easier to trap and more vulnerable to disease in stagnant pools. The ephemeral nature of floodplain refugia meant that hatchlings often faced periods of isolation, overcrowding, or inundation, with mortality spikes reflected in growth rings and population structure of fossil assemblages. Conversely, some species evolved strategies to synchronize hatching with receding water levels or to exploit niches in elevated hummocks, revealing a sophisticated interplay between life history and environmental timing. Detritus-based feeding networks intensified, with scavengers, small reptiles, and insects converting the abundant, decaying matter into essential nutrients. Fallen leaves, drowned ferns, and dead animal matter accumulated in pockets of standing water, creating nutrient-rich microhabitats. Fossilized coprolites and gut contents demonstrate that many organisms became specialized for exploiting this detritus, forming the backbone of emergent food webs that relied less on live prey and more on the omnipresent decay of the drowned landscape. These networks supported both generalist and specialist species, driving unexpected evolutionary trajectories under the constraints of 2 million years of precipitation. Temporary high-ground refugia became critical arenas for reproduction, feeding, and social interaction, shaping population distributions. Small rises, old river levees, or patches of resistant rock provided islands of stability in a world otherwise dominated by standing water. Fossil evidence shows clusters of nests, burrows, and trackways on these elevated areas, indicating that even the most mobile species had to contend with constrained space for vital life functions. Competition for these refugia likely influenced territorial behaviors, mating systems, and social hierarchies, adding yet another layer of complexity to survival in this saturated world. Throughout this continuous wet realm, thriving meant negotiating a seamless mix of land and water, where speed and strength alone were insufficient. Every aspect of anatomy, behavior, and life history was sculpted by the hydrological regime, and each adaptation became a narrative of endurance, ingenuity, and evolutionary opportunity. From ambush predators lying in flooded depressions to herbivores negotiating treacherous mud, the dance of life in a perpetually inundated world demonstrates that environmental extremity can be both a crucible and a laboratory for survival. And as rivers braided, ponds expanded, and landscapes shifted beneath unceasing rainfall, the stage was fully set for species increasingly bound to aquatic or semi-aquatic life, foreshadowing the next wave of evolutionary specialization. The rise of amphibian megapredators. Emerging from the flooded banks, a metopusaurid's flattened skull cut through the water with silent precision, barely disturbing the surface of the sprawling wetland. Its dorsally positioned eyes scanned the shallow pools for movement, while wide, powerful jaws waited to snap shut on unwary prey. Fossils show these amphibians could reach lengths of over 6 meters, their elongated bodies perfectly streamlined for a world that had become a liquid labyrinth. The relentless rainfall had fused rivers, lakes, and marshes into interconnected networks, creating hunting grounds that terrestrial predators could scarcely navigate. In this environment, success demanded a mastery of water, a precision born of evolution sculpted by eons of uninterrupted inundation. Along the sinuous waterways, temnospondyls patrolled their territory with a mix of stealth and patience. Their movements were deliberate, powered by limbs that alternated between swimming strokes and short bursts along muddy banks. Evidence from well-preserved trackways suggests that even juvenile individuals learned quickly how to exploit the rhythm of rising and falling waters to ambush fish, small reptiles, and invertebrates. Paleontologists have noted the intricacy of their sensory systems. Lateral line-like structures and pressure-sensitive skin allowed detection of vibrations, a vital adaptation in turbid, sediment-rich waters where visibility was limited. In such a permanently wet world, hunting strategies became a direct reflection of environmental constraints, intertwining physiology and behavior. Fossilized skulls reveal a mosaic of adaptations, from reinforced jaw musculature capable of withstanding repeated, forceful bites to narrow, elongated snouts suited for snapping prey out of submerged vegetation. The cranial anatomy shows not only evolutionary ingenuity, but also evidence of convergent solutions among disparate aquatic lineages. Teeth were arranged to grip rather than slice, optimized for catching slippery prey in fast-moving currents. Within these bone beds, paleontologists have identified assemblages hinting at repeated occupation of certain floodplain regions, implying that these megapredators were not just opportunistic hunters, but structured their life cycles around stable wetland hotspots. In a landscape defined by water, anatomy became behavior, and behavior became survival. Seasonal fluctuations in water levels dictated reproductive timing, driving complex nesting behaviors on islands and elevated mounds that persisted through short-term floods. Embryonic and larval fossils suggest rapid growth phases, with juveniles reaching substantial sizes in a few years, minimizing vulnerability in predator-saturated waters. These life history strategies exemplify how an unbroken hydrological pulse could shape every aspect of development. The convergence of flooded terrain, stable breeding grounds, and abundant prey created ecological niches that these amphibians exploited with remarkable efficiency, ensuring dominance across vast areas of Triassic wetlands. Submerged vegetation and fallen logs became natural hunting blinds, providing both cover and elevated vantage points. Ambush strategies relied on patience, timing, and the subtle interplay of water flow and camouflage. Fossil evidence shows cranial depressions consistent with sensory organs adapted for detecting movement under murky waters, allowing predators to strike with astonishing speed. In contrast, smaller prey species evolved evasive behaviors, including synchronized schooling, cryptic coloration, and burrowing into sediment, highlighting a dynamic predator-prey arms race. The wetlands themselves became a living laboratory, continuously shaping morphology, behavior, and survival tactics. Bone beds indicate mass gatherings, suggesting either seasonal migrations, social behaviors, or congregation in response to environmental cues. Some assemblages contain hundreds of individuals, hinting that interactions were more complex than simple competition. These gatherings may have also allowed for cooperative defense against other large aquatic predators or facilitated mating rituals within confined floodplain networks. The dense clustering of individuals underscores how the hydrological constancy of the environment not only sustained life, but also influenced population structure, social organization, and the spatial distribution of species across an ever-changing terrain. The chemical composition of preserved sediments offers a glimpse into oxygen-poor microhabitats that shaped respiration and metabolic strategies. Analysis of iron and sulfur isotopes reveals prolonged anoxic conditions in some basins, indicating that metaposaurids and temnospondyls had to tolerate low oxygen levels or exploit shallower, oxygenated layers. Gill-like adaptations and cutaneous respiration in some taxa allowed them to thrive where less specialized vertebrates would have perished. Water chemistry, therefore, was not merely a backdrop, it acted as a sculptor, influencing physiology, ecology, and evolutionary trajectories in tandem with predation and competition. Predatory success was inseparable from water depth and clarity, demonstrating the fine-scale coupling between physiology and hydrology. Fossilized stomach contents, trackways, and even preserved bite marks illustrate that hunting techniques varied with microhabitat, ranging from shallow, sediment-choked pools to deep, flowing channels. Amphibian megapredators adapted continuously to shifting conditions, exploiting opportunities presented by turbidity, water flow, and prey distribution. Their dominance exemplifies how extreme, constant environmental pressure can accelerate specialization, favoring traits that merge physical prowess with environmental awareness. Competition among megapredators sculpted community structure with size, speed, and stealth, determining survival outcomes. Ecological partitioning allowed multiple large predators to coexist by targeting different prey, utilizing distinct microhabitats, or hunting at varied times within the hydrocycle. This balance between competition and coexistence mirrors the broader dynamics of Triassic ecosystems, where constant water coverage simultaneously constrained and liberated evolutionary possibilities. The wetlands became an arena for evolutionary ingenuity, rewarding adaptation, experimentation, and opportunistic behaviors in ways impossible on drier, unstable terrains. Amid the endless aquatic expanse, life was reshaped, producing species exquisitely adapted to a planet soaked for eons. Every skull, limb, and behavioral adaptation narrates a story of resilience and innovation in the face of relentless hydrological pressure. As metoposaurids and temnospondyls patrolled their flooded dominions, the stage was set for the eventual emergence of terrestrial reptiles that would struggle to navigate the increasingly watery landscape, forcing further evolutionary divergence. Water, once an environmental backdrop, had become the defining force of life itself, dictating which forms would thrive, which would adapt, and which would vanish into the sediment-laden depths of history. Early dinosaurs and archosaurs struggling through the wet. Through waterlogged plains, proto-dinosaurs tested each step, their feet sinking into mud that clung like glue, challenging every stride and demanding adaptations that minimized energy loss. Their lightweight skeletal frames, including hollowed limb bones and elongated metatarsals, offered some relief, allowing for more agile navigation of these saturated terrains. Fossil trackways, preserved in compacted clay and silts, reveal patterns of careful, calculated movement rather than unrestrained locomotion, highlighting how these early archosaurs were forced to rethink speed, balance, and energy expenditure. The constant moisture dictated not just movement, but also the spatial distribution of populations, encouraging clustering around raised, relatively stable landforms. Every undulating ridge and pool created a landscape of constant uncertainty, demanding careful navigation and influencing social behavior. Evidence from fossilized nesting mounds shows that early dinosaurs and their relatives sought higher ground to protect eggs from inundation, often clustering multiple nests on the same small islands of safety. Sedimentology studies indicate that rainfall frequency and intensity forced repeated nest abandonment, driving evolutionary pressures for flexible reproductive timing and accelerated development of hatchlings. These mounds also created microhabitats where moisture-loving plants flourished, further influencing feeding strategies, shelter availability, and predator-prey dynamics. By interpreting the terrain, proto-dinosaurs had to anticipate changes that could occur within hours, a cognitive and behavioral challenge as significant as the physical one. Trackways preserved in clay tell of twisting, hesitant movements, showing herds negotiating shifting terrain with an intelligence born of necessity. Footprints reveal uneven spacing and abrupt changes in direction, suggesting reactive decision-making to avoid both deep mud and submerged obstacles. Comparisons of different ichnofossils suggest a stratification of species use. Smaller forms stuck to higher, firmer ground, while larger, heavier archosaurs ventured into softer sediments, likely exploiting aquatic prey or scavenging stranded organisms. The muddy labyrinth served as both trap and opportunity, forcing early dinosaurs to integrate sensory perception, environmental awareness, and cautious movement into every step. Elevated mounds became precious refuges, where nests rose just above the ever-encroaching floodwaters, forming centres of life amid surrounding wetlands. Vegetation on these mounds not only protected waterlogging, but also offered concealment from emerging aquatic predators, such as temnospondyls and large amphibians. The reproductive success of these proto-dinosaurs depended on their ability to time egg-laying to coincide with slight recessions in water levels, showcasing an intricate interplay between rainfall patterns and life cycles. Even minimal elevation could mean the difference between an entire brood surviving or perishing beneath relentless precipitation. Shadows of predators lingered along submerged pathways, exploiting the limited visibility imposed by endless rain and opaque floodwaters. Fossil evidence of tooth marks and gnawed bones in sediment layers indicates that hunting strategies had adapted to these murky conditions, favouring ambush and opportunistic feeding over prolonged chases. Predators likely relied on vibration detection and chemical cues, while prey species evolved alert postures, herd behaviours, and early warning strategies, demonstrating a rapid evolutionary feedback loop driven by environmental extremity. Seasonal and daily rainfall fluctuations further influenced predator activity, with heavy downpours both obscuring movement and forcing temporary retreats. This constant tension forged an ecosystem where awareness, caution, and responsiveness became as critical as strength or speed. Rapid juvenile growth patterns indicate a life strategy honed for unpredictable and hazardous conditions, ensuring that individuals reach functional size quickly enough to escape frequent floods, predation, and disease proliferation in saturated soils. Bone histology from specimens in floodplain deposits shows accelerated ossification rates, particularly in limb elements, reflecting a physiological response to environmental stress. Nest success rates, tracked through sediment analysis, suggest that mortality was disproportionately high in early stages, creating strong, selective pressure for rapid development and early mobility. These pressures produced a generation of highly adaptable young dinosaurs capable of negotiating treacherous terrains sooner than might have been expected in drier conditions. Growth trajectories thus reveal the intimate relationship between climate, habitat, stability, and life history strategy. Reconfigured waterways fragmented habitats, forcing both herbivorous and carnivorous reptiles into new migratory patterns and resource utilization strategies. Sedimentological mapping shows repeated avulsions, channel shifts, and pond formation that disrupted established territories, forcing species to explore unfamiliar terrain. Paleoecological reconstructions suggest that flood-adapted plants flourished in newly formed shallow basins, creating temporary feeding grounds for herbivores. Carnivores, in turn, adapted by tracking these ephemeral concentrations of prey, often following the shifting margins of wetlands over kilometers of soggy land. Movement through this dynamic landscape required constant assessment, further highlighting the selective pressures imposed by the hydrological regime on terrestrial vertebrates. Sudden surges of rainwater reshaped the land, washing away nests and scattering vulnerable populations, leaving behind fossilized traces of disrupted ecosystems. Sediment layers show rapid deposition events consistent with flash flooding, which caused abrupt mortality in both adult and juvenile populations. The repeated loss of nesting sites created a mosaic of evolutionary pressures, promoting mobility, site fidelity when possible, and opportunistic colonization of new areas. These episodic events also concentrated nutrients and carcasses in low-lying pools, providing transient feeding opportunities that were quickly exploited by scavengers and predators alike. Limbs adapted for boggy movement reveal how early archosaurs balanced speed, power, and stability while traversing soft substrates. Morphological studies of fossilized limb elements indicate specialized joint articulation, broad foot surfaces, and muscle attachment patterns that countered the sinking risk of saturated soils. Comparative analysis with semi-aquatic contemporaries shows a spectrum of adaptations, with some species favoring sprinting across firmer micro-highlands, while others developed stamina for wading long distances. The physical challenges of wetland locomotion were therefore a critical driver of skeletal evolution, influencing not only individual survival but also long-term lineage success. These anatomical innovations allowed early dinosaurs to exploit niches that would otherwise have been inaccessible in such a relentlessly wet environment. Success depended on interpreting every ripple, mound, and mud channel, a skill central to survival in this drenched world. Evidence from sediment-embedded trackways indicates that decision-making involved both instinctual responses and learned behaviors, with juveniles observing adults in critical navigation strategies. Water depth, flow velocity, and mud consistency all became integral variables in habitat selection, foraging efficiency, and predator avoidance. These interactions reveal a planet where cognition and environment were inseparable, where survival relied on continuous engagement with a landscape that was both home and adversary. Every inch of this ever-shifting terrain demanded constant adaptation, with each movement carrying evolutionary weight. Proto-dinosaurs and early archosaurs were forced to innovate, respond, and endure, translating environmental challenge into anatomical and behavioral sophistication. The endless rainfall, omnipresent mud, and ephemeral refuges together created a crucible in which survival required a complete integration of body, mind, and instinct. And as wetlands expanded, channels shifted, and rainfall persisted, these terrestrial pioneers forged the foundations for future evolutionary triumphs, leaving behind a fossil record that narrates both struggle and resilience in a world defined by water. Freshwater systems rewired by endless storms. The braided rivers twisted into sprawling labyrinths, their boundaries merging and separating with every pulse of rainfall. What had once been individual channels now formed an interconnected aquatic network stretching across continents, the continuous influx of water reshaping topography on a massive scale. Satellite patterns of the past, preserved in sediment layers, reveal how the hydraulic pulse of unending storms guided the movement of channels, forcing rivers to braid, meander, and occasionally merge into shallow inland seas. Each confluence carried nutrients, sediments, and organisms across distances unimaginable to the terrestrial fauna struggling along the saturated margins, connecting ecosystems that had previously been isolated by dry land. The sheer scale of these super wetlands transformed not only the flow of water, but also the evolutionary landscape of every species dwelling within their grasp. Sediment-laden currents carved temporary islands, each one a fleeting refuge for flora and fauna navigating the new aquatic maze. Elevated mounds of silt and clay, formed during lulls in rainfall, offered critical breathing space for terrestrial plants attempting to survive constant inundation. Fossilized impressions of root mats and seed deposits indicate that these islands became critical staging grounds for growth and reproduction, a precarious sanctuary amid ceaseless floodwaters. Aquatic organisms exploited submerged debris and detritus accumulating along these mini plateaus, turning them into microhabitats rich in food and shelter. These ephemeral refuges were as transient as the rivers themselves, appearing and vanishing with seasonal flows, yet their presence shaped local community structures and influenced survival strategies on both small and large scales. These ancient mud layers capture the imprint of continuous water movement, revealing the slow but relentless shaping of the land. Stratigraphic sequences in lowland basins demonstrate cycles of sediment deposition interspersed with fine-grained silt and organic matter, reflecting prolonged standing water conditions. These records illuminate the gradual vertical aggradation of floodplains, the lateral expansion of water bodies, and the erosion of older surfaces under continuous hydraulic stress. The isotopic signatures preserved in these sediments, particularly of carbon and oxygen, indicate repeated episodes of supersaturation, high humidity, and fluctuating water chemistry. Through these chemical and physical archives, scientists can reconstruct the hydrodynamic regime, showing that the continent-scale wetlands were not fleeting phenomena, but enduring features shaped by persistent precipitation. Nutrient distribution shifted unpredictably, creating hotspots of biological productivity and barren zones alike. Areas of sediment deposition concentrated minerals, feeding rapid growth of aquatic plants, algae, and microinvertebrates, which in turn attracted herbivores and small predators. Conversely, erosion-prone zones were stripped of topsoil and nutrients, leaving exposed clay beds where vegetation struggled to establish, and aquatic populations were limited. The complex interplay between sediment transport, mineral deposition, and organism activity created a patchwork of ecological opportunity, one in which mobility, opportunism, and specialization dictated survival outcomes. Rivers became living laboratories, illustrating how chemical fluxes and mechanical forces collaborated to shape both habitat and behavior in a continually wet world. Inland seas expanded into shallow networks, connecting previously isolated wetlands and permitting long-distance dispersal of aquatic species. Fish, amphibians, and semi-aquatic reptiles traversed these new corridors, colonizing territories that would have been unreachable in drier epochs. Fossil evidence suggests that previously endemic species suddenly appear in distant basins, mirroring the hydraulic pathways traced by sediment deposits. In turn, predators tracked these populations, exploiting corridors that allowed for efficient hunting, while herbivores and detritivores adjusted their ranges to match the shifting availability of food. These extended networks created super wetland corridors that rewired ecosystems across entire continents, linking water chemistry, sedimentation, and biological communities in a manner that blurred the distinction between local and regional habitats. Oxygen levels in stagnant channels fluctuated dramatically, forcing adaptations in respiration and metabolism among resident fauna. Dense vegetation, high organic load, and slow-moving waters generated hypoxic microenvironments, favouring species capable of air-breathing or facultative aquatic respiration. Fossils with modified gill or lung structures, combined with trace evidence of burrowing and surface ventilation, suggest a widespread evolutionary response to low oxygen conditions. Animals that could not adjust were confined to marginal refuges or faced localized extinction, creating strong selective pressures that reinforce the emergence of specialized physiologies. These dynamics illustrate the direct linkage between hydrology, water chemistry, and evolutionary innovation, showing how persistent storms did not merely shape landscapes, they sculpted life itself. Riparian plants developed anchoring strategies against constant inundation, their root systems simultaneously stabilizing and modifying sediment. Tree ferns, horsetails, and primitive gymnosperms produced deep, fibrous roots that could resist lateral displacement while also trapping silt and organic debris to create mini elevations within floodplains. The interaction between vegetation and water flow created feedback loops. Stabilized sediment allowed larger plants to establish, which in turn altered current paths, slowed erosion, and fostered nutrient accumulation. Fossilized root traces and sedimentary bedding plains reveal the co-evolution of plant communities and hydrological dynamics, highlighting the intricate choreography between biology and environment during the formation of these super wetlands. Seasonal pulses of water created cycles of inundation and temporary exposure, driving migration and breeding behaviors across taxa. Amphibians, fish, and semi-aquatic reptiles timed their reproduction to coincide with rising waters, exploiting flooded zones for egg deposition while minimizing predation risk. Migratory patterns of herbivores and small carnivores reflected temporary corridors moving between nutrient-rich floodplains and more stable upland refuges. These rhythms, encoded in both behavior and physiology, illustrate how organisms integrated environmental signals over annual cycles, converting the constraints of continuous rainfall into reproductive opportunity. Life, in these conditions, was defined by its responsiveness to water's mercurial presence. Geochemical markers preserved in sediments reveal how floodwaters concentrated minerals, subtly altering soil chemistry over wide regions. Layers rich in iron, phosphorus, and trace elements show accumulation in standing water zones, fueling plant growth and influencing microbial activity. These chemical concentrations, in turn, affected the nutritional value of plants and prey, creating cascading effects throughout trophic networks. Fossilized microfauna within these deposits indicate population booms and busts corresponding to these chemically enriched patches, demonstrating that hydrology dictated ecosystem productivity as decisively as topography or climate. Through this intertwining maze of rivers and channels, evolutionary pressures were shaped as much by shifting waters as by predation. Physical forces, erosion, deposition, water velocity, are intertwined with chemical and biological processes, ensuring that survival, reproduction, and dispersal are inseparable from the watery landscape. The relentless hydraulic engine molded anatomy, behavior, and life cycles, producing species tuned as much to water chemistry and flow dynamics as to competition or predation. Every organism became part of a network defined by both living and non-living forces, a testament to the power of persistent rainfall to orchestrate continental-scale ecological and evolutionary outcomes. Finally, as this planetary-scale web of freshwater merged, species adapted, perished, and radiated across unprecedented hydrological corridors. The sprawling super wetlands were no longer merely landscapes, they were active participants in life's history, shaping ecosystems, evolutionary pressures, and ecological possibilities. The chemical, physical, and biological threads of this system intertwined to create a world where water dictated existence at every level, preparing the stage for the eventual inundation of coastlines and the next dramatic reshaping of Earth's surface and its life. Oceans suffocating under sediment and freshwater. Turbid rivers poured into the shallow seas, carrying mud, silt, and organic detritus in an unstoppable cascade, turning once clear waters into opaque corridors of sediment. Coastal shelves, long accustomed to periodic flooding, were overwhelmed as continuous rainfall funneled an unprecedented volume of terrestrial material into the oceans, thickening the water column and smothering habitats once teeming with life. Currents carried clay particles hundreds of kilometers offshore, forming muddy deltas that buried benthic organisms and altered the physical structure of the seabed, effectively rewriting the rules of survival for all marine life. Evidence from laminated shales and sandstone layers captures this relentless deposition, each stratum recording episodes of turbidity and oxygen deprivation in precise geological time. Salt and fresh water collided, forming stratified layers that trapped oxygen near the surface while suffocating the depths, creating pockets where even hardy invertebrates could no longer respire. This stratification, driven by constant runoff, prevented vertical mixing, effectively decoupling nutrient cycles and altering the flow of dissolved gases necessary for life. As rivers continued to discharge high loads of sediment, the upper waters became oxygen-rich, yet laden with fine particles, while deeper layers stagnated, darkened, and fermented under anaerobic conditions. Geochemical analyses of black shales from this interval reveal sulfur isotope excursions consistent with prolonged anoxia, confirming that these coastal waters had shifted from vibrant habitats to environmental dead zones. Fossil assemblages reveal sudden disappearances of bivalves, brachiopods, and other sensitive taxa, leaving only resilient survivors capable of tolerating hypoxic and turbid conditions. In some paleontological sites, mass mortality layers show dense accumulations of dead mollusks and crinoids, abruptly halting normal ecological succession. Opportunistic species, such as small gastropods and hardy polychaetes, persisted in patches where oxygen was sporadically available, their survival testament to evolutionary flexibility in the face of continuous stress. Each assemblage offers a stark contrast to the pre-flood communities, illustrating that environmental extremity could reset entire ecosystems within decades, geologically speaking. Sediment plumes, visible even in paleogeographic reconstructions, spread across continental shelves, smothering benthic habitats and reshaping the topography of shallow seas. Channels that had once funneled clear water now carried a slurry of fine particles, burying coral-like structures and stromatolitic mats that had persisted for millennia. These sediment layers, sometimes meters thick, blanketed soft sediments, creating a fresh surface for colonization while simultaneously erasing prior ecological memory. Fossilized burrows become abruptly truncated in these deposits, showing that bioturbation ceased almost entirely during peak sedimentation, leaving the ocean floor a layered record of repeated drowning events. Microbial mats thrived in oxygen-depleted zones, dominating seafloor surfaces where larger life had vanished, converting detritus into biomass in a stark, low-diversity landscape. Cyanobacteria, sulfur bacteria, and other extremophiles exploited chemical gradients, forming layered structures that trapped nutrients and further intensified hypoxia. In some locales, mats reached tens of centimeters in thickness, preserving microfossils that reveal both rapid growth and the absence of competing animals. These microbial assemblages effectively became the architects of a new ecosystem, illustrating how life can seize opportunity even under the harshest environmental constraints. Chemical signatures in limestone and shale record the rapid deposition of phosphorus, iron, and organic carbon, marking ecological stress across broad scales. Elevated phosphorus concentrations fueled localized microbial productivity, while excess iron catalyzed further anoxic reactions in sediments. Carbon isotope excursions document increased burial of organic matter, a consequence of both terrestrial runoff and the death of previously abundant marine organisms. Collectively, these chemical markers provide a direct line of evidence linking continental hydrology with marine ecosystem collapse, showing that the fate of life in the oceans was inseparable from the persistent storms on land. Turbulent estuaries became crucibles for opportunistic species, forcing evolutionary experimentation under extreme conditions. Fish capable of tolerating low oxygen and high turbidity expanded their ranges, while others perished in areas of stagnant water. Crustaceans that could burrow or cling to stable substrates persisted, illustrating that behavioral innovation was as important as anatomical adaptation. These refuges, scattered and ephemeral, became centers of survival and eventual recolonization, demonstrating that even during profound ecological upheaval, life found microhabitats to endure and evolve. Waves of hypoxia expanded seaward, with every current and eddy exacerbating the suffocating impact of runoff, creating gradients of mortality that shaped population structures. The interaction between freshwater input, sediment load, and oceanic currents created dynamic zones of partial survival, where only mobile or tolerant organisms could persist. This hydrodynamic complexity meant that even minor shifts in rainfall or river discharge could produce cascading effects across kilometers of coastal habitat. Geophysical models suggest that these processes operated continuously over hundreds of thousands of years, reinforcing the persistent dominance of water-driven ecological pressures. Bioturbation almost ceased, leaving sedimentary layers pristine and directly readable as a record of environmental collapse. Trace fossils are sparse or absent in many deposits, indicating that worms, bivalves, and other sediment-dwelling organisms had been driven from the substrate. This absence highlights the extreme severity of stress imposed by unbroken freshwater and sediment influx, offering a rare glimpse into how entire functional groups of marine life can be temporarily extinguished. Such pristine layers serve as geological time capsules, preserving chemical and biological data for future reconstruction of ancient catastrophes. In isolated refuges along the flooded coasts, life persisted only in pockets where chemistry, flow, and luck coincided to offer refuge, emphasizing that survival was dictated less by competition than by chance and environmental tolerance. These refugia provided the seeds for post-crisis recovery, harboring lineages that would eventually re-expand into the newly stabilized ocean. Across continents, the interplay between relentless storms, sediment deposition, and coastal chemistry created a world where water dictated not only the surface of the land, but the very fate of life at the margins of the seas. In this drowned oceanic landscape, the legacy of unbroken rainfall and continental runoff would be etched into stone, preserving a chemical and ecological memory that whispers of a planet continually reshaped by water. The planet that forgot how to breathe. Clouds pressed low over continents, carrying oxygen-depleted air across forests and wetlands, a sky thick with water vapor and chemical tension. Beneath it, the world's life moved cautiously, each breath drawn through air that was no longer reliably nourishing, each inhalation carrying the subtle risk of suffocation. Rivers and flooded plains emitted faint, sulfur-rich odors, the unseen consequences of prolonged rainfall and decaying organic matter, while animals adapted behaviorally and physiologically to the air itself. The planet's once constant atmosphere had become a volatile medium, its composition oscillating in concert with storms, sediment, and microbial activity across a hydrologically rewired surface. High-resolution ice and sediment proxies reveal abrupt spikes in carbon dioxide and methane flux, painting a chemical portrait of an air thick with greenhouse gases. These excursions, mirrored in the isotopic signatures of plants and soil, tell of a world where the atmosphere was actively shaped by rainfall, runoff, and volcanic emissions. Even subtle shifts in oxygen content had cascading consequences for metabolism, mobility, and reproductive timing, favoring species able to cope with episodic hypoxia. Trees, amphibians, and early reptiles, each faced invisible stressors, navigating landscapes drenched in water and atmospheres strained by chemistry. Within this chemically volatile air, microclimates emerged, some pockets relatively breathable, others lethally stagnant, forcing life into localized refuges. Atmospheric circulation slowed under constant rain, trapping heat and gases near the surface, creating stagnant layers that accentuated oxygen depletion in low-lying basins. Fog hung persistently over wetlands, blending with smoke and steam from distant volcanic activity, and the air itself seemed to pulse with latent energy. Predators and prey alike altered their activity cycles, with crepuscular or nocturnal behaviors emerging not solely from predation risk, but as a physiological response to poor oxygen availability. Evolution, as much as ecology, was dictated by the composition of the very air. Even small hills and ephemeral ridges became lifelines, their higher ventilation offering temporary sanctuary for species otherwise struggling to survive in the suffocating lowlands. The chemical composition of rainwater mirrored the evolving imbalance, subtly altering soils and water chemistry. Nutrients became diluted, pH levels shifted, and trace elements fluctuated, producing stress on plant communities, even in areas not directly flooded. These chemically mediated pressures created feedback loops. Weakened vegetation contributed more organic detritus to wetlands, further depleting oxygen locally and releasing additional CO2 back into the atmosphere. Each droplet falling from a storm cloud was both a product and a driver of planetary chemical reorganization, reminding life that every aspect of the environment, from soil to sky, had become a force to contend with. Fossilized plant stomata indicate prolonged stress from hypoxic and CO2 (SN) rich conditions, revealing an intimate connection between atmospheric change and terrestrial adaptation. Stunted growth rings, altered leaf morphology, and decreased stomatal density record the physiological toll of the environment. Early herbivorous archosaurs and amphibians exhibited slower growth rates, while opportunistic species exploited niches in chemically altered microhabitats. Even temporary clearings, previously safe for nesting or grazing, became hazardous, their conditions shifting unpredictably with rainfall, sediment deposition, and decomposing matter. Microbial mats in wetlands adjusted to fluctuating redox levels, mediating local oxygen availability and creating isolated refuges of survivable chemistry. Their activity influenced nitrogen and sulfur cycles, stabilizing microenvironments just enough to sustain larvae, amphibians, and small reptiles. Sedimentary evidence of mats, coupled with geochemical signals, indicates these microbial communities were essential for maintaining pockets of life as the global atmosphere became increasingly unreliable. Their role underscores how microscopic life could dictate survival outcomes for larger organisms in extreme conditions, transforming wetlands into a patchwork of microhabitats that buffered but never eliminated the stress of oxygen deprivation. Volcanic aerosols interact with water vapor, amplifying greenhouse effects and altering atmospheric density. Fine ash and sulfates reflected sunlight unevenly, creating pockets of warming and cooling, while simultaneously changing precipitation patterns. This interplay affected wind currents, humidity, and temperature gradients across the continents, producing regional variations in oxygen depletion and CO2 accumulation. Life became a constant negotiation with both visible storms and the invisible chemistry of the air, forced into a rhythm of adaptation dictated by planetary scale forces. Birds had yet to evolve, but their ancestors, proto-archosaurs, navigated treacherous air currents, relying on instinctive, precise movement to survive each day. Paleogeographic reconstructions suggest that low-lying regions, experienced stagnant air layers, suffocating terrestrial organisms and reshaping species distributions. Populations retreated to higher elevations or ephemeral ridges, where ventilation was sufficient to support normal respiration. This migration, driven by chemistry rather than predation or competition, reshaped food webs and social behaviors. Seasonal or episodic floods, once the dominant concern, became secondary to the fundamental challenge of simply extracting oxygen from the air. Small amphibians burrowed deeper, reptiles became more cautious, and life at the edges of ponds and rivers faced daily calculations of risk and reward. Carbon and sulfur isotope excursions trace the coupling between continental runoff and atmospheric chemistry, demonstrating how water, rock, and life formed a single, interconnected system. Heavy rainfall transported sediments rich in organic carbon and sulfur into wetlands and shallow seas, releasing gases as decomposition progressed. Atmospheric oxygen declined in concert with these processes, while CO2 and methane levels rose, creating feedback loops that reinforced environmental stress. The Earth's atmosphere, once a stable backdrop, had become an active participant in evolutionary and ecological outcomes. The chemical memory of this era would echo in fossils, sediments, and isotopic records for hundreds of millions of years, marking the profound influence of unbroken rainfall on global biogeochemistry. Life everywhere contended with an invisible force. Air itself was reshaped into both barrier and medium for survival. Some species developed behavioral adaptations, others physiological adjustments, larger lungs, slower metabolism, or reliance on aquatic habitats to buffer against oxygen scarcity. Predators measured success not only in capture, but in endurance under chemically challenging conditions. Each day became a contest not of strength alone, but of adaptation, timing, and the ability to sense subtle shifts in air composition. Every breath taken, every movement made, was a negotiation with a planet that had forgotten how to breathe, revealing the subtle yet profound ways that relentless rainfall and hydrological engineering could reach from the sky to the lungs of every organism below. The Great Reassembly, ecosystems reforged under perpetual storms. Pushed by relentless rainfall, survivors navigated newly flooded corridors, discovering niches previously inaccessible. The constant presence of water transformed every movement into a negotiation with the environment. Terrestrial pathways were now ephemeral, often submerged under ankle to knee-deep mud, while low-lying depressions became semi-permanent ponds. Species that had once thrived on dry land were forced to either retreat to elevated ridges or adapt to an ever-changing wet matrix, demonstrating that resilience was no longer measured by brute force, but by flexibility and situational awareness. Each flooded ravine and sediment-laden channel dictated the potential for life, reshaping interactions among organisms at scales from individual to population. Rooted plants bent and twisted, their architectures reshaped by the constant deluge, providing scaffolds for burgeoning communities. Trees with shallow roots were uprooted, leaving behind woody debris that became islands of habitat for insects, amphibians, and small reptiles. Dense mats of ferns, horsetails, and seed ferns sprawled across inundated soils, their vascular systems pressed into a new equilibrium with unceasing moisture. These plants were both victims and facilitators of change. While some perished beneath standing water, others exploited the new hydrological conditions to expand aggressively, altering canopy density, light penetration, and the flow of nutrients across the floodplain. Submerged hills and temporary ridges became life-saving refuges, hosting dense assemblages of reptiles, amphibians, and invertebrates. Elevated microhabitats allowed nesting and breeding in otherwise inhospitable terrain, forming concentrated pockets of biodiversity that contrasted sharply with the surrounding wetlands. Fossil evidence hints at repeated occupation of these raised zones, suggesting that animals developed site fidelity based on subtle topographical cues. In these refuges, herbivores grazed selectively on surviving vegetation, while predators lurked in the edges of water, exploiting prey forced to navigate narrow, precarious paths. The interplay of water, land, and life created an ever-shifting tapestry of ecological opportunity and constraint. Predator-prey dynamics shifted, with ambush strategies exploiting water currents, sediment flows, and vegetation patterns. Semi-aquatic predators could approach silently beneath shallow water, detecting vibrations through mud and submerged roots, while prey species evolved heightened sensory awareness, quicker reflexes, and behavioral innovations like group movement or temporary burrowing. Early archosaurs and proto-dinosaurs struggled to negotiate this new environment, often forced to alter hunting tactics entirely, foraging in flooded areas only at dawn or dusk, when light conditions reduced exposure to aquatic ambush predators. Over millennia, these pressures carved clear ecological boundaries between aquatic, semi-aquatic, and terrestrial forms, forging evolutionary divergence that would shape entire lineages. Trackways etched in mud reveal that species experimented with group movement, foraging patterns, and synchronized migrations under hydrological constraints. Herding behavior became advantageous where water currents could separate individuals, and cooperative vigilance allowed prey to exploit flooded corridors with slightly reduced risk. Similarly, predators that coordinated movements through shallow streams or used natural vegetation to funnel prey had higher survival success. These behavioral patterns, now fossilized in both physical tracks and sedimentary context, demonstrate that the rainfall-induced wetland matrix was not a passive backdrop, but an active agent of selection, shaping life at both the individual and community levels. Microbial mats flourished across shallow floodplains, mediating oxygen levels, nutrient cycling, and the availability of microhabitats. Cyanobacteria, algae, and other microorganisms formed dense films in calm waters, providing food for invertebrates and influencing sediment deposition. Their metabolic activity also contributed to localized hypoxia, particularly in stagnant pools, creating chemical refuges for species tolerant of low oxygen conditions, while limiting competitors. The microbial foundation of these flooded landscapes shows that survival and ecological complexity depended not only on large vertebrates, but on the unseen networks of microorganisms that subtly sculpted the physical and chemical characteristics of habitats. Water chemistry, enriched with decomposing organic matter, dictated where populations thrived or dwindled, creating a mosaic of success and failure. Nutrient-laden runoff and organic decomposition created patchy areas of productivity and scarcity. Some species capitalized on these zones, growing faster, reproducing earlier, and forming dense local populations, while others perished or migrated. Isotopic signatures preserved in sediment cores show fluctuations in carbon, oxygen, and sulfur that correspond to these high and low productivity zones, providing a record of ecological experimentation in a constantly dynamic hydrological theatre. Behavioral innovation emerged as a necessity. Temporary arboreal refuges, burrowing into raised soil, and nocturnal activity mitigated environmental pressures. Reproductive strategies are adapted to water permanence and unpredictability, with species producing eggs capable of surviving short inundations or migrating to small, isolated patches for nesting. Predatory species adjusted hunting schedules, learned to exploit waterborne pathways, and modified postures or locomotion to navigate unstable mud and submerged roots. Even seemingly minor innovations like perching on fallen logs or temporary island hopping had outsized effects on survival probabilities, emphasizing the fine balance between innovation and extinction. Sedimentary layering preserves snapshots of dynamic food webs, showing predators, herbivores, and detritivores interacting in unprecedented ways. Layers of mud, silt, and sand, punctuated by root traces and trackways, capture moments of ecological interaction frozen in time. Large amphibians, small reptiles, insects, and plants created a lattice of dependency and competition, illustrating the intimate connections between species responding to the same hydrological stressors. Each stratum tells a story of predation, foraging, or avoidance, revealing how new ecological architectures emerged from constant rainfall and unrelenting environmental pressure. Evolution, ever experimental, sculpted species into new forms, behaviors, and ecologies uniquely adapted to a planet perpetually ruled by rain. Over thousands of generations, physiological changes, enhanced lung capacity, altered limb proportions, flattened bodies for swimming, or extended sensory systems reflected the interplay of survival and environmental constraint. Entire clades radiated into new niches created by the flood-dominated landscape, producing ecosystems that would have been impossible under previous, drier conditions. Water was both sculptor and canvas, and the life that endured bore its imprint in form, function, and behavior, a testimony to resilience under relentless hydrological pressure. For 2 million years, the skies never relented, and life was forced to bend, adapt, or vanish beneath the endless pulse of rain. This deluge was more than weather, it was a sculptor of ecosystems, a test of endurance, and a crucible of evolution, reshaping the very essence of life on Earth. In the silent layers of mud and sediment, the memory of a planet drowned, yet alive, is preserved, whispering of struggle, resilience, and transformation. As the rain finally eased, the world it forged remained forever, changed an echo of nature's relentless power. If you felt this journey, consider liking, subscribing, or sharing your reflections below.